Close your eyes if you'd like to. Not just yet, if you're still reading these words, but soon. Tonight, we're going to travel somewhere darker and stranger than almost anywhere else in the universe. We're going to travel toward a black hole, one of the most extreme, most mysterious objects that physics has ever discovered. And we're going to ask a question that has quietly haunted scientists for over a century. What's actually inside one? Let that question rest in your mind for a moment, soft and dark, like a single drop of ink spreading slowly through still water. We're not going to rush toward an answer tonight. We're going to walk there gently, the way you might walk down a quiet, unlit hallway at night, one careful step at a time, letting your eyes slowly adjust to the dark. Along the way, we'll talk about event horizons and singularities, and why the very equations that describe gravity so beautifully everywhere else in the universe seem to simply give up, right at the center of a black hole, refusing to tell us what's really there. There is something wonderfully calming about a mystery this deep. It means the universe still has secrets. It means that even now, with all our telescopes and satellites and supercomputers, there remain quiet, dark rooms we haven't fully entered yet. And there's a kind of peace in that, if you let it be peaceful. A permission to simply wonder, without needing to solve anything before you're allowed to rest. So settle in now. Let your shoulders drop, let your breathing slow, and let's drift together, gently, toward the darkest objects in the known universe. To understand what's inside a black hole, we first have to understand where black holes come from. And that story begins, gently, with the life and death of a star. Stars, for most of their long lives, exist in a delicate, patient balance. Deep in their cores, immense pressure and heat fuse hydrogen atoms into helium, releasing enormous amounts of energy in the process. This energy pushes outward in every direction, like a constant, gentle exhale. At the same time, the star's own enormous mass pulls inward, under the relentless, patient force of gravity, the same force that holds you gently against your bed right now. For millions or billions of years, depending on the star, these two forces, the outward push of fusion and the inward pull of gravity, remain in a careful, quiet balance, and the star simply shines, steady and calm, the way it has for most of its existence. But nothing lasts forever, not even stars. Eventually, a star begins to run low on the fuel needed to keep that outward push going. For very massive stars, stars many times heavier than our own sun, this ending can become dramatic. As fusion slows and finally stops, there's nothing left to resist gravity's patient, relentless pull. The outer layers of the star, no longer held up by outward pressure, begin to fall inward, faster and faster, collapsing toward the core. For some stars, this collapse ends in a colossal explosion called a supernova, one of the brightest, most violent events in the universe, briefly outshining an entire galaxy. The outer layers of the star are blasted outward into space, scattering heavy elements, carbon, oxygen, iron, gold, elements that would later become part of planets, oceans, and even living things, across the surrounding darkness. But at the very center, where the star's core was most tightly packed, something quieter, and in some ways stranger, happens. If the remaining core is massive enough, heavier than about 3 times the mass of our sun, packed into an impossibly small space, no known force in the universe can stop its collapse. Not the pressure of atoms resisting each other, not the strange quantum forces that normally keep matter from crushing infinitely close together. Gravity simply wins, completely, and finally, and the core collapses inward, and inward, and inward, without anything left to stop it. This is the birth of a black hole. I want you to picture this slowly, gently, as if watching it from a great, safe distance. A massive star's core, once the size of a small planet, collapsing down and down, past the size of a city, past the size of a mountain, past the size of anything you could hold in your hand, collapsing toward a point so small, so dense, that the very fabric of space and time around it begins to bend and warp in ways that ordinary physics struggles to describe. Around this collapsing core, something new forms, an invisible boundary in space, a point of no return. Physicists call this boundary the event horizon, and it's really the true surface of a black hole, if you can call it that at all. Once anything, light, matter, even information itself, crosses this boundary, it can never come back out. Not because of some invisible wall or barrier, but because inside that boundary, gravity has bent space itself so severely that every possible path, every direction you could travel, leads only further inward. The way every path down a steep, one-way slide leads only to the bottom. Rest with that image for a while tonight. A star, born from a cloud of gas billions of years ago, living quietly for ages, shining steadily, and then, in its final moments, collapsing so completely that it creates a boundary in space itself, beyond which nothing can ever return. This is where our story begins tonight. Not with the black hole itself just yet, but with the quiet, patient, almost dreamlike collapse that creates one. Let that collapse rock you gently now, the way a stone sinks slowly through deep, still water, drifting downward, unhurried, toward the dark. Let's slow down now and sit for a while with the event horizon itself, because I think it's one of the most beautifully strange ideas in all of physics, and it deserves a slow, careful look. Imagine, for a moment, throwing a ball straight up into the air. It rises, slows, and eventually falls back down, pulled by Earth's gravity. Now imagine throwing that ball harder and harder still. Eventually, if you could throw it fast enough, about 11 kilometers per second for Earth, the ball would be moving quickly enough to escape Earth's gravity entirely, sailing off into space, never to fall back down. This speed is called the escape velocity, and every massive object in the universe has one, depending on its mass and its size. Now imagine a much stranger object, one so massive and so incredibly compact that its escape velocity exceeds the speed of light itself. Since nothing in the universe, as far as we currently understand physics, can travel faster than light, this means that nothing, no rocket, no particle, not even a beam of light itself, could ever move fast enough to escape from within a certain distance of this object. That distance, that invisible boundary, is the event horizon. It's important to pause here and gently correct a common misunderstanding, one that even shows up in some well-meaning documentaries. The event horizon is not a physical surface, not a wall, not a membrane you could touch or bump into. It's simply a boundary in space, a mathematical and physical threshold, beyond which the curvature of space-time becomes so extreme that all paths, quite literally all possible paths through space and time, lead inward toward the center rather than outward toward escape. Picture, if it helps, a great slow whirlpool in the middle of a vast calm river. Far from the whirlpool's center, a boat can paddle freely in any direction, upstream, downstream, sideways, wherever it likes. But as it drifts closer to the whirlpool's center, the water begins to move faster and faster, and at a certain distance, the current becomes so strong that no matter how hard the boat's engine works, it can no longer paddle away. Past that point, the boat is drawn inevitably inward, not because some wall stops it from leaving, but because every direction the water flows leads only closer to the center. The event horizon works in something like this way, except what's flowing isn't water, but space itself, being drawn steadily inward by the black hole's immense gravity. Once you cross that boundary, moving away is not simply difficult. It becomes, according to our best understanding of physics, genuinely, physically impossible. Every direction that you might once have called forward or outward now points inward instead, toward the center, the way. Every direction from the North Pole points south. This is part of why black holes are called black in the first place. It's not that they're painted a certain color, or that they absorb light the way a dark surface does. It's that no light can escape from within the event horizon at all. Any light produced inside is trapped forever, unable to climb back out against the overwhelming pull of gravity. From the outside, a black hole appears as a region of utter, complete darkness, a silhouette against the stars, betrayed only by its gravitational effects on the matter and light around it. Let this boundary settle into your mind now, gently, not as something frightening, but simply as one of the strangest, most elegant lines ever drawn in the universe, an invisible edge hanging quietly in space, marking the last possible place from which anything could ever return. Somewhere right now, scattered across our galaxy and countless others, These silent boundaries hang in the dark, patient and still, waiting, asking nothing of anyone, simply existing. The way a locked door exists, whether or not anyone ever tries its handle. Let's imagine, gently and safely, from the comfort of your bed, what it might actually be like to fall toward a black hole. Not to frighten you, but because I think the physics involved is strange in a way that's genuinely worth slowing down for. The way you might slow down to look closely at a very unusual flower you've never seen before. Picture a very large black hole, the kind found at the center of galaxies, sometimes called a supermassive black hole, with a mass millions or even billions of times greater than our sun. Because these black holes are so large, their event horizons are correspondingly enormous, and, this is the strange part, the tidal forces near their event horizon are actually much gentler than you might expect. Gentler, in fact, than the tidal forces near the much smaller event horizon of a black hole formed from a single collapsed star. If you were to fall toward a supermassive black hole, feet first, in the early stages, you might not even notice anything unusual happening to your body at all. You would simply drift, weightless, the way an astronaut drifts in orbit, falling steadily toward the event horizon, watching the black hole grow larger and larger in your view, blotting out more and more of the starry sky behind it. As you approach the event horizon itself, something curious would happen to how you perceive time, and how the universe outside would appear to you. According to Einstein's theory of general relativity, gravity doesn't just bend the paths of light and matter through space. It also affects the flow of time itself. Clocks closer to a massive object run slower, from the perspective of someone far away, than clocks farther from it. This effect, called gravitational time dilation, becomes extraordinarily pronounced near a black hole's event horizon. If a friend stayed behind, watching you fall from a safe distance, they would see something stranger, and stranger the closer you got to the horizon. Your movement would appear to slow down more and more, as if time itself were stretching out for you. Light leaving your body would take longer and longer to climb back out against the black hole's gravity, growing dimmer and shifting toward red. The way light shifts when its source is moving away. From your friend's perspective, you would never actually appear to cross the event horizon at all. You would simply seem to slow and fade and dim, approaching the horizon forever, without ever quite seeming to reach it, frozen, in their view, at the very edge of no return. But from your own perspective, falling gently through space, none of this stretching or dimming would be apparent at all. Your own clock, your own heartbeat, your own breathing would feel completely normal to you. You would simply continue falling, smoothly and continuously, crossing the event horizon without any dramatic flash, without any wall to bump into, without in fact any local sign at all that you had crossed a boundary of any significance. The event horizon, remember, isn't a physical surface. From the inside, in that first moment, everything might feel remarkably ordinary. There's something quietly poetic in this strange mismatch between the two perspectives. The friend watching from a distance, seeing you slow and fade forever, suspended at the edge of the horizon, and you yourself, falling gently onward, feeling nothing unusual at all, crossing into a realm from which, if the event horizon truly is what our physics says it is, you could never send word back. I share this with you tonight, not to unsettle you, but because I think it's one of the strangest, gentlest reminders in all of physics that time itself is not the fixed, universal river we often imagine it to be in ordinary life. It bends and stretches and slows, depending on where you are and how fast you're moving, and how close you are to something as massive as a black hole. Your own experience of time right now, as you drift towards sleep, is itself flowing at its own particular pace, shaped gently by the Earth's own modest gravity, by your own modest speed through space, unimaginably far from anything as extreme as an event horizon. Let that thought rock you now, the way a boat rocks gently on calm water. Time, flexible and strange at the deepest levels of physics, and yet, right here, right now, flowing steadily and gently for you, carrying you softly toward rest. I promised earlier that we would walk through this material gently, without unnecessary alarm, and I want to keep that promise now, even as we talk about a term that sounds a little dramatic at first: spaghettification. This word, despite its playful sound, describes something physicists take quite seriously: the way intense tidal forces near certain black holes can stretch an object, gradually pulling it long and thin. The way you might stretch a piece of soft dough between your hands, pulling it longer and longer, thinner and thinner. Here's why this happens, explained slowly. Gravity's pull grows stronger the closer you are to a massive object. If you were falling feet first toward a very small, very dense black hole, one formed from a single collapsed star, rather than the supermassive kind we discussed a moment ago, the gravitational pull on your feet, being slightly closer to the black hole than your head, would be noticeably stronger than the pull on your head. This difference in pull, however small, is called a tidal force, and near a small, dense black hole, it can become extraordinarily strong, stretching an object along the direction of the fall while gently compressing it from the sides, the way stretching dough narrows even as it lengthens. For a black hole formed from a single collapsed star, this stretching could become quite severe even before reaching the event horizon, which is why, for such black holes, falling in would indeed be an intense and ultimately fatal experience for any observer, human or otherwise. But, and this is the gentler, quieter part of the story, for the truly enormous, supermassive black holes found at the centers of galaxies, this tidal stretching is much, much gentler, precisely because their event horizons are so much larger. The difference in gravitational pull between your head and your feet, near the event horizon of a supermassive black hole, can be so small as to be barely noticeable at all, even as you cross the boundary itself. It's only much later, much deeper inside, as you approach the very center, that the tidal forces would eventually become overwhelming. I share this distinction with you tonight because I think it says something quietly beautiful about how physics actually works: precise, careful, full of nuance, resisting the simple, dramatic story in favor of the more accurate, more interesting one. Not every fall toward a black hole looks the same. Scale matters, size matters. The universe, even in its most extreme corners, remains patient and specific, offering different experiences under different conditions, rather than a single, uniform terror. Let this careful, nuanced picture settle over you now, gently, the way a careful explanation settles a worried mind more effectively than a vague, frightening rumor ever could. The universe's extremes are strange, yes, but they are governed by precise, knowable rules, worked out patiently over generations by careful scientists, rather than by chaos or randomness. There is something calming in precision, even when the subject itself sounds intense. Understanding, gently applied, tends to soften fear into simple, quiet curiosity. Breathe slowly now, in and out. Let your own body, resting safely and gently on solid, unremarkable, wonderfully ordinary Earth, feel the calm, steady pull of a very modest gravity. Nothing at all like the extremes we've been discussing. Just a soft, familiar weight, holding you kindly in place as you drift towards sleep. If you listen to an earlier story from this channel about what existed before the Big Bang, this next idea might feel familiar to you, like returning to a room you've visited before. Its furniture rearranged just slightly, but its general shape still recognizable. At the very center of a black hole, according to the mathematics of general relativity, lies something called a singularity, a point, or perhaps a region, where the curvature of space-time becomes, according to the equations, infinite. Density becomes infinite. The strength of gravity becomes infinite. And when a physicist's equations produce an answer of infinity, it's very often a sign that the equations themselves have reached the edge of where they can be trusted, rather than a sign that nature is truly physically infinite in that spot. Think back, if it helps, to that old image of an explorer's map, with careful detail drawn along the known coastlines, and then, beyond the edge of what anyone had actually charted, simply blank parchment, or the honest words, "Here be dragons." The singularity at the heart of a black hole functions much like that blank edge on the map. It's not that physicists believe reality actually becomes infinitely dense at a single point. It's that general relativity, our best theory of gravity, was never designed to describe matter compressed to such an extraordinary degree. And at that scale, another set of rules should take over. The strange, granular rules of quantum mechanics, governing the world of the very, very small. Just as with the Big Bang singularity, physicists do not yet have a complete, tested theory that successfully merges general relativity with quantum mechanics, a full theory of quantum gravity. Without that theory, we cannot say, with real confidence, what is actually happening at the center of a black hole. The singularity predicted by today's equations may simply be a sign of our theory's limits, a placeholder marking we don't yet know, rather than a true description of physical reality. This means that tonight, when we ask what's inside a black hole, the most honest answer, spoken plainly and without embarrassment, is we don't fully know, not with complete certainty, what exists at the very center. We have a good, well-tested understanding of the region approaching the center, the event horizon, the strange bending of space and time nearby, the way an object would experience its fall. But the deepest heart of a black hole remains genuinely unmapped territory, a puzzle actively being explored by physicists today, using some of the most sophisticated mathematics ever developed. I find something quietly comforting in this admission of uncertainty, and I hope you can find some comfort in it too tonight. It means black holes remain genuinely mysterious, even to the scientists who study them most closely. It means there is still real, active wondering happening in the world, right now, about one of the strangest objects the universe has ever produced. And it means that the story we're telling together tonight isn't a story with a tidy, fully solved ending. It's a story still being written, slowly, carefully, page by careful page, by patient researchers working at the very edge of human knowledge. Rest with that unfinished quality for a while. Not every story needs a complete ending to be worth telling. Some of the best stories are the ones still unfolding, quietly, patiently, in the background, while we ourselves drift off to sleep, trusting that the story will still be there, waiting, whenever we're ready to return to it. Let's take a slower, gentler look, now at what it actually means, physically, for gravity to bend space and time. Because I think a clear picture here will make everything else about black holes feel a little less abstract, and a little more like something you can hold quietly in your mind as you drift towards sleep. Before Einstein, gravity was understood quite reasonably as a kind of invisible pulling force, reaching out across empty space to attract one object toward another, the way Isaac Newton had described it centuries earlier. This picture worked remarkably well for most everyday purposes, and still does. It's how engineers calculate the orbits of satellites, how we predict the tides, how we understand a dropped apple falling to the ground. But Einstein's general relativity offered a deeper, stranger, and ultimately more accurate picture. In this view, gravity isn't really a force reaching out across space at all. Instead, massive objects gently curve the very fabric of space and time around themselves, and other objects moving nearby simply follow the curved paths laid out for them by this bent, warped fabric. The way a marble rolling across a stretched, sagging bedsheet naturally curves toward a heavy object resting in its center, not because the object is reaching out and pulling the marble, but because the sheet itself is bent, guiding the marble's path along its natural curve. Picture this now, softly. Space and time together, forming a single, flexible fabric, sometimes called space-time, stretching in every direction throughout the universe. Ordinary objects, like planets and stars, create gentle, shallow dips in this fabric, subtle curves that guide the orbits of nearby objects without dramatically distorting the fabric itself. Our own sun creates just such a gentle dip, guiding Earth's steady, graceful orbit. A black hole, though, represents something far more extreme. Because its mass is compressed into such an extraordinarily small space, it creates a dip in space-time so deep, so steep, that it's less like a shallow bowl and more like a bottomless, narrowing well. Its walls growing steeper and steeper the closer you approach the center, until, at the event horizon, the well becomes so steep that nothing, not even light itself, has enough energy to climb back out. This is why light itself bends near a black hole, curving along the warped fabric of space exactly as any other object would, and why light directly at the event horizon becomes trapped entirely, unable to find any path leading back outward. It's also why the region very close to, but just outside, a black hole's event horizon appears warped and distorted, when viewed carefully through a telescope. Light from stars behind the black hole gets bent around it, sometimes creating strange, curved, mirror-like images, a phenomenon called gravitational lensing. I want you to hold this picture gently in your mind now, not as frightening, but simply as beautiful. An enormous, invisible fabric stretching across the entire universe, dipping and curving around every star, every planet, every galaxy, guiding the graceful, patient dance of everything in the cosmos, from the gentle orbit of the moon around the Earth to the terrifyingly steep well surrounding a black hole's event horizon. You too, right now, are resting gently within a small dip in this same fabric, the Earth's own modest curve in space-time, holding you softly in place. The same fundamental physics that shapes black holes also shaping, ever so gently, the quiet comfort of your own bed tonight. Let's rest for a while on the different kinds of black holes that exist across the universe, because I think there's something soothing in cataloguing them slowly, the way you might slowly sort a collection of smooth stones by size, turning each one over gently in your hand before setting it down. The most common type, and the one we've mostly been discussing so far, is called a stellar mass black hole, formed from the collapse of a single massive star's core, as we described earlier tonight. These black holes typically have masses, somewhere between about 5 and several dozen times the mass of our Sun, compressed into a region only a few kilometers across, smaller in some cases than a city. Astronomers believe there may be hundreds of millions of stellar mass black holes scattered throughout our galaxy alone, mostly quiet and undetected, drifting silently through space, their presence betrayed only on the rare occasions when they interact gravitationally with a nearby star, or with another black hole. Then there are supermassive black holes, the giants of the black hole family, found at the centers of most large galaxies, including our own Milky Way. These behemoths can have masses ranging from hundreds of thousands to many billions of times the mass of our Sun. Despite their enormous mass, because it's spread across a correspondingly larger event horizon, their density is actually far lower than that of a stellar mass black hole. In fact, the very largest supermassive black holes have an average density lower than that of air, spread thin across an event horizon that could span a distance larger than our entire solar system. Astronomers still don't fully understand how these giants grew so large, so quickly in the early universe, and it remains an active, ongoing area of research. Between these two extremes, astronomers have found tantalizing evidence, though not yet fully confirmed, of intermediate mass black holes, somewhere between stellar and supermassive in size, possibly forming a missing link that helps explain how modest stellar mass black holes might eventually grow, over billions of years, into the supermassive giants found at galactic centers. There's also a more speculative, theoretical category called primordial black holes, which, if they exist, wouldn't have formed from collapsing stars at all, but rather from extremely dense fluctuations in the very early universe, mere fractions of a second after the Big Bang, when the cosmos was hot, chaotic, and unevenly distributed enough that small pockets of space might have collapsed directly into black holes, without ever passing through a stellar phase at all. These primordial black holes, if they exist, could theoretically range from incredibly tiny, even smaller than an atom, up to many times the mass of our Sun. Some scientists have even wondered whether primordial black holes might make up some portion of the universe's mysterious dark matter, though this remains an open, actively debated question, still being tested against observational evidence. And finally, there's a purely theoretical category, sometimes discussed by physicists studying quantum gravity, called micro black holes. Extraordinarily small, extraordinarily short-lived black holes that might, in principle, form under very particular, very extreme conditions, evaporating away almost instantly, due to a process we'll discuss a little later tonight, called Hawking radiation. No such micro black holes have ever been observed, and it remains uncertain whether they could form under any realistic conditions at all. But they occupy an interesting corner of theoretical physics nonetheless. Let this quiet catalogue settle over you now, gently, the way a collection of smooth stones, sorted patiently by size, might rest undisturbed on a shelf, each one different, each one interesting in its own particular way. None of them urgent, none of them demanding immediate attention, simply existing, quietly, in their careful, sorted rows. Before we continue further into tonight's story, let's pause for a little while, here in the quiet middle of our journey, and simply let everything settle. You've traveled a long way already tonight, through the slow, patient collapse of a dying star, across the strange boundary of an event horizon, through the odd mismatch between falling and watching, through gentle explanations of stretching and bending, and through a careful, unhurried tour of the different families of black holes scattered throughout the universe. That's a great deal of strange, vast territory to have walked through gently, together. It's all right if your mind feels a little hazy now, a little soft around the edges, images blending together the way dreams often blend just before you finally fall asleep. There's no test at the end of tonight's story. Nothing you need to remember, no detail you need to hold on to tightly. What matters is simply this: that you've spent some quiet time tonight resting your mind on one of the strangest, most extreme objects the universe has ever produced, and that in doing so, you've joined a very old, very human tradition of looking outward into darkness and wondering gently what might be there. Let your body sink a little deeper now into your mattress. Let your hands go soft and heavy. Let your face relax, your forehead smooth, your jaw loose, your eyelids heavy, heavier still. We have more of the story left tonight, a few more quiet rooms to wander through together, but there's no rush at all. If you drift off now, that's more than all right. That's exactly what this story is for. And if you're still here, still listening, still gently curious, then let's continue, softly, into the next room. Let's walk now into one of the strangest, most hotly debated puzzles in modern physics. One that connects black holes to some of the deepest questions about the nature of reality itself. The black hole information paradox. To understand this puzzle, we need to sit for a moment with a principle that lies at the very heart of physics, something so fundamental that scientists rarely even think to state it explicitly. The way you rarely think to state that the ground will hold you up when you take a step. This principle says that information, in a very deep physical sense, is never truly destroyed. If you burn a piece of paper, the information describing that paper, the exact position and motion of every atom of ash and smoke and light produced by the fire, is, in principle, still out there, scattered and scrambled almost beyond recognition, but not actually erased from the universe. A being with impossibly perfect knowledge and calculation could, in principle, trace all of that scattered information backward and reconstruct exactly what the original piece of paper looked like. This principle matters gently for our story tonight, because black holes seem to challenge it in a very direct, very puzzling way. When matter falls into a black hole, crossing the event horizon, it seems to disappear from the observable universe entirely, its information seemingly locked away forever behind that boundary of no return, inaccessible to anyone on the outside. For a long time, physicists were relatively comfortable with this idea. The information wasn't destroyed, they reasoned, it was simply hidden, tucked away behind the event horizon, safe and sound, even if inaccessible. But in the 1970s, the physicist Stephen Hawking made a discovery that complicated this picture significantly. One we'll explore in a little more detail shortly. He showed that black holes aren't quite as eternal and unchanging as once thought. Due to quantum effects near the event horizon, black holes very slowly radiate energy away, over unimaginably long timescales, and eventually they should fully evaporate, disappearing entirely. This raised a deeply puzzling question. If a black hole eventually evaporates completely, disappearing from the universe, what happens to all the information that fell into it over its long lifetime? If that information simply vanishes along with the black hole itself, it would represent a genuine violation of one of physics's most cherished principles. A true, permanent loss of information from the universe. Something most physicists find deeply uncomfortable, almost unthinkable. The way you might feel deeply unsettled by the idea that basic arithmetic could simply stop working in certain corners of reality. This puzzle, known as the black hole information paradox, has occupied some of the finest minds in theoretical physics for decades now. And while there is still no fully settled, universally agreed upon resolution, there has been genuine, patient progress. Many physicists now believe, based on careful theoretical work, that information is not actually lost when a black hole evaporates, but is instead somehow encoded, subtly and intricately, within the radiation the black hole emits as it slowly fades away, smuggled out, so to speak, in a form so scrambled and complex that it would be almost impossibly difficult to decode, and yet, in principle, still present, still preserved, still part of the universe's careful, patient bookkeeping. Exactly how this smuggling happens, in precise physical detail, remains an area of active, ongoing research, involving some of the most sophisticated mathematics in all of modern physics, including ideas from string theory and something called the holographic principle, which we'll gently explore in a little while. I share this puzzle with you tonight, not to trouble your rest, but because I find something quietly moving in it. It reflects physicists' deep, careful commitment to the idea that the universe is, at its core, orderly and consistent, that nothing is ever truly, senselessly lost, even in the most extreme, most violent corners of existence. Even a black hole, this puzzle suggests, however dark, however mysterious, however final it may seem from the outside, may ultimately preserve, in some deeply hidden, deeply scrambled way, every last trace of everything that ever fell into it. Let that thought settle over you gently now, like a soft, reassuring blanket. Nothing is ever truly, completely lost, not even into the darkest, most extreme corners of the universe. Everything, in some deep, careful sense, is remembered, preserved, held, even when we ourselves can no longer see or access it directly. Let's linger a while longer on the discovery we touched on a moment ago, because I think it's one of the most beautiful, most unexpected results in all of black hole physics. The realization that black holes are not, in fact, perfectly, eternally black. In 1974, Stephen Hawking, drawing on the strange rules of quantum mechanics we discussed briefly in an earlier story from this channel, made a remarkable theoretical discovery. Recall that the quantum vacuum, even in seemingly empty space, is never perfectly still. Tiny fluctuations of energy are constantly, spontaneously appearing and disappearing, forming brief pairs of particles that almost always vanish again within an instant, too quickly to ever be directly observed under ordinary circumstances. Hawking realized that near the event horizon of a black hole, something curious could happen to these fleeting particle pairs. Occasionally, one particle from such a pair might fall into the black hole, crossing the event horizon, while its partner escapes outward, into the wider universe. From the perspective of a distant observer, this would look exactly like the black hole itself, emitting a faint stream of particles, a slow, steady trickle of radiation, now known as Hawking radiation. This discovery had a profound and somewhat startling implication. If a black hole is slowly emitting particles outward, it must, ever so slightly, be losing energy in the process. And since energy and mass are deeply connected, according to Einstein's famous relationship between the two, this means the black hole itself must be very slowly losing mass over time, shrinking, almost imperceptibly, particle by particle, across spans of time so enormous, they make even the age of the universe look brief by comparison. For most black holes we know of, this evaporation process is almost unimaginably slow. A black hole with the mass of our Sun, for instance, would take far, far longer than the current age of the universe, trillions upon trillions of years, to evaporate away completely through Hawking radiation alone. Larger, more massive black holes evaporate even more slowly still, actually taking longer, counterintuitively, the more massive they are, because a larger event horizon produces an even fainter, gentler trickle of radiation. But smaller black holes, if they exist, would evaporate much more quickly, and theoretically, the very last moments of a black hole's evaporation, as it shrinks down toward nothing, would become faster and faster, the process finally ending in a faint, final burst of radiation, and then, quite simply, nothing at all. The black hole entirely gone, its event horizon closed, its long, patient darkness finally, gently extinguished. There's something deeply, quietly beautiful in this picture, I think, especially at this hour, as your own body settles toward its own kind of quiet rest. Even the darkest, most permanent-seeming objects in the universe are not in fact eternal. Even black holes, given enough time, an amount of time so vast it barely fits into ordinary human comprehension, will eventually fade and dim and finally, gently, disappear. Their long-held darkness slowly, patiently returning to the light from which, in a sense, it originally came. Nothing in this universe, it seems, not even the deepest darkness, lasts forever. Everything eventually, in its own time, at its own pace, settles and fades and rests. I want to pause here and talk with you for a little while, quietly, about something that isn't purely physics, but that matters just as much, especially at night, when big, unanswered questions tend to feel a little heavier, a little larger, than they do in the busy light of day. It can feel uncomfortable at first to sit with a question as strange as what's inside a black hole, and to hear again and again that nobody fully knows the answer. We're used to questions having answers, tidy and complete, but the biggest questions, the ones that sit right at the very edge of human understanding, don't always work that way. And I think there's a real gentle comfort available to us if we can learn to rest peacefully within that uncertainty, rather than fighting against it. Consider how far our understanding of black holes has already come in a relatively short span of time. A little over a century ago, black holes existed only as a strange, almost accidental mathematical curiosity, emerging from Einstein's newly published equations of general relativity, a solution so extreme that even Einstein himself doubted such objects could really exist in nature. For decades, many physicists treated black holes as little more than a mathematical oddity, unlikely to have any real physical counterpart in the actual universe. It wasn't until later in the 20th century that astronomers began finding genuine observational evidence for black holes, first indirectly, through their gravitational effects on nearby stars and gas, and then, remarkably, in 2019 directly, when an international collaboration of scientists released the first ever image of a black hole's silhouette, a faint, glowing ring of light surrounding a perfectly dark shadow, captured using a network of telescopes spanning the entire Earth, working together as a single, planet-sized instrument. A few years later, they captured an image of the black hole at the very center of our own Milky Way galaxy, a faint glowing ring surrounding the quiet darkness at our galaxy's heart. And in 2015, scientists using an instrument called LIGO made another extraordinary discovery, directly detecting for the very first time ripples in space-time itself, gravitational waves, produced by two black holes spiraling into each other and merging far across the universe, billions of years ago. This detection opened up an entirely new way of observing black holes, listening for the ripples they send through space-time itself, rather than only watching for light. Human understanding of black holes has expanded dramatically, again and again, decade after decade, each new discovery revealing that these objects are stranger, more real, and more richly detailed than physicists had once dared to imagine. There is no reason at all to think this process has stopped, or that we've reached some final complete understanding in our own particular lifetime. The deepest mystery of all, what truly happens at a black hole's very center, may well be answered, at least in part, by scientists working right now, refining their mathematics, building ever more sensitive instruments, patiently gathering evidence that will eventually, someday, shift our uncertain hypotheses into something closer to confident understanding. You get to hold that unfolding mystery gently tonight, not as a source of worry, but as a kind of quiet privilege. You are alive at a moment in human history when we know more about black holes than any humans who came before us, and yet we still stand, together, at the edge of a genuinely enormous mystery. There is something wonderfully humbling and wonderfully peaceful in that. You don't have to solve it tonight. You only have to rest gently at its edge, the way scientists themselves, at the end of a long day of careful work, must eventually set down their calculations and rest too. Breathe in slowly, and out. In, and out. Let's walk gently now into one more strange and beautiful idea. One that grew directly out of physicists' careful attempts to resolve the information paradox we discussed earlier, the holographic principle. This idea is genuinely one of the strangest in modern theoretical physics. So let's approach it slowly, without rushing. The way you might approach an unfamiliar, oddly shaped object in a darkened room, feeling your way carefully around its edges before trying to understand its whole shape. Ordinarily, we assume that the amount of information something can contain depends on its volume. A larger box, we naturally assume, can hold more information than a smaller one, the way a larger bookshelf can hold more books. But when physicists carefully studied the behavior of black holes, calculating precisely how much information a black hole's event horizon could contain, they found something deeply surprising. The amount of information a black hole can hold isn't proportional to its volume at all, but rather to the surface area of its event horizon. This might sound like a small technical detail, but its implications are genuinely staggering. It suggests that all of the information describing everything that has ever fallen into a black hole, everything about its entire three-dimensional interior, might somehow be fully completely encoded on its two-dimensional surface, its event horizon, the way an entire three-dimensional scene can be encoded on the flat, two-dimensional surface of a hologram, that shimmering image that seems to have real depth and volume, even though it's actually printed on a flat piece of film. Some theoretical physicists have taken this idea even further, proposing what's called the holographic principle as a much broader, more general feature of the universe, not just of black holes. The idea that all the information contained within any given region of space might, in some deep mathematical sense, be fully described by information encoded on the boundary surrounding that region, rather than truly, independently existing within its full three-dimensional volume. In this view, our entire three-dimensional universe and everything happening within it, including you, right now, resting quietly in your bed, might, in some deep mathematical sense, be describable as a kind of projection, arising from information encoded on some distant, two-dimensional boundary, the way a hologram creates the convincing illusion of three-dimensional depth from a flat surface. I want to be gentle and honest with you here, as always. The holographic principle remains a genuinely speculative, though mathematically serious and actively researched, idea. It has proven remarkably useful as a theoretical tool, helping physicists make real progress on some of the hardest problems in quantum gravity, including aspects of the black hole information paradox. But whether it represents a literal, complete description of how our actual universe fundamentally works remains a matter of ongoing research and genuine scientific debate. Still, I find something quietly wondrous in simply holding this idea for a while tonight, letting it drift gently through your mind without needing to fully resolve it. The universe, even in its most basic architecture, might be far stranger, far more interconnected, and far more elegantly structured than our ordinary, everyday intuitions would ever have led us to expect. Depth, volume, even the solid three-dimensional world you experience around you every day, might, at the deepest level, be a kind of beautiful, intricate projection, arising from something simpler, flatter, and more fundamental. Let that strange, gentle idea rock you now, the way a hologram catches the light and shifts, depending on the angle from which you view it, revealing new depths, new colors, new dimensions, the closer and more patiently you look. Let's drift now toward another idea that often appears alongside black holes in popular imagination, though it remains, I want to be honest with you, considerably more speculative than almost everything else we've discussed tonight: the idea of wormholes. A wormhole, in the language of general relativity, refers to a hypothetical shortcut through space-time, a kind of tunnel or bridge connecting two distant points in space, or even, in some theoretical versions, two distant points in time, allowing, in principle, a much shorter path between them than the ordinary distance would suggest. Picture, if it helps, a flat sheet of paper representing the fabric of space, with 2 points marked at opposite ends. Traveling between them, in the ordinary way, means crossing the entire flat sheet. But if you gently fold that sheet of paper so the 2 points touch, and then poke a small hole connecting them directly, you've created a shortcut, a tunnel bridging what would otherwise be a very long journey. The mathematics of general relativity does technically allow for solutions resembling such wormholes, sometimes called Einstein-Rosen bridges, after Einstein and the physicist Nathan Rosen, who studied them together in the 1930s. But there's an important, gentle caveat here, one worth resting on carefully. These theoretical wormhole solutions, as originally studied, would be extraordinarily unstable, collapsing shut almost instantly, far too quickly for anything, even light, to pass through them. Keeping a wormhole open long enough to actually travel through would require an exotic form of matter or energy with very unusual properties. Something physicists sometimes call negative energy density, a concept that does have some genuine grounding in certain very specific quantum phenomena, but which has never been observed to exist in anything close to the quantities or configurations that would be needed to stabilize a wormhole large enough and long enough to be useful for travel. So while wormholes remain a beloved and genuinely mathematically legitimate feature of general relativity's equations, and a wonderful source of inspiration for thoughtful science fiction, most physicists remain quite doubtful that traversable wormholes, ones stable enough to actually journey through, exist anywhere in our actual universe, or could ever realistically be constructed. There is, however, a fascinating and much more theoretical idea connecting wormholes back to black holes specifically, sometimes discussed under the playful shorthand ER equals EPR, proposed by physicists Juan Maldacena and Leonard Susskind. This idea suggests a deep, surprising mathematical connection between wormholes, on the one hand, and a strange quantum phenomenon called entanglement, on the other, where two particles become linked in such a way that measuring one instantly affects our knowledge of the other, no matter how far apart they are separated in space. This remains a highly theoretical, actively researched corner of physics, offering tantalizing hints about how gravity, quantum mechanics, and the very structure of space-time itself might be more deeply, more strangely connected than previously imagined. I offer you this idea tonight gently, as a beautiful, speculative thread, rather than a settled fact, a reminder that even at the frontiers of serious, careful physics, there remains room for genuinely strange, genuinely wonder-inducing possibilities, still being explored, still being tested, still very much unresolved. Let your mind rest now on the simple, gentle image of a folded sheet of paper. Two distant points brought close together, not as a literal claim about how you might someday travel across the universe, but simply as a reminder that even vast distances, even seemingly impossible separations, might, in the deepest mathematics of our universe, be more closely connected than they first appear. Let's rest for a while on something wonderfully concrete tonight. A break from pure theory and speculation. What astronomers have actually directly observed about black holes using real telescopes, gathering real data, here in our own corner of the universe. For a long time, black holes could only be detected indirectly, through their gravitational influence on nearby matter. Astronomers would notice a star orbiting what appeared to be empty space, wobbling in a way that could only be explained by the gravitational pull of an invisible, massive companion. By carefully studying these wobbles, scientists could estimate the mass of the unseen object. And when that mass turned out to be too large and too compact to be explained by any known type of star, black holes became the most likely explanation. Astronomers have also observed black holes surrounded by what's called an accretion disk, a swirling, glowing disk of gas and dust, slowly spiraling inward toward the event horizon, heated by intense friction to extraordinarily high temperatures as it falls, often glowing brightly in X-rays long before it finally crosses the horizon and disappears. These glowing accretion disks have provided some of the strongest indirect evidence for black holes throughout the latter half of the 20th century. Then, as we touched on earlier, came April 2019, a genuinely historic moment in the history of astronomy. An international team of scientists, working together as part of a project called the Event Horizon Telescope, released the very first direct image ever captured of a black hole's silhouette, specifically the supermassive black hole at the center of a galaxy called Messier 87, some 55 million light-years away. The image showed a faint glowing ring of superheated gas, distorted and bent by the black hole's immense gravity, surrounding a dark, perfectly circular shadow at its center, the unmistakable silhouette of the event horizon itself, exactly as physicists had long predicted. To capture this image, Scientists had to link together radio telescopes scattered across the entire planet, from Hawaii to Spain to the South Pole, synchronizing them with extraordinary precision to work together as a single telescope effectively the size of the entire Earth. It was, quite genuinely, one of the most ambitious scientific collaborations in human history, requiring years of careful planning, painstaking data collection, and patient analysis. In 2022, the same team released a second historic image, this time of Sagittarius A Starst, the supermassive black hole at the very center of our own Milky Way galaxy, a mere 26,000 light-years from Earth. Though closer than the black hole in Messier 87, imaging it presented its own unique challenges, since gas swirling around Sagittarius A moves and changes shape much more quickly, requiring especially clever techniques to capture a clear, stable image. And then, as we also touched on earlier, there's the remarkable achievement of LIGO and its sister observatories, first detecting gravitational waves directly in 2015, ripples in spacetime itself, produced by two black holes, each many times the mass of our Sun, spiraling together and merging in a cosmic collision over 1 billion years ago, releasing more energy in a fraction of a second than all the stars in the observable universe combined. An event whose gentle, fading ripple finally reached Earth, stretching and squeezing the fabric of space by an almost unimaginably tiny amount, detected by instruments sensitive enough to measure a change in distance thousands of times smaller than the width of a single proton. I share these real, concrete achievements with you tonight because I think there's something deeply reassuring in remembering that everything we've discussed tonight isn't purely abstract mathematics, floating free of any connection to the real, observable universe. Real telescopes, built and operated by real, patient scientists, have genuinely seen the shadow of a black hole's event horizon. Real instruments have genuinely felt the ripple of two black holes colliding billions of years ago in some distant corner of the cosmos. The strange, extreme physics we've been exploring tonight is not merely theoretical. It is out there, real and observable, patiently confirmed, piece by careful piece, by dedicated people working at observatories and laboratories all around our world. Let that quiet confirmation settle over you now, like a gentle, reassuring hand resting softly on your shoulder. The universe's strangest mysteries are not simply stories we tell ourselves in the dark. They are real, patiently, carefully confirmed, again and again, by careful people doing careful, patient work. Let's slow down again now, and spend a while, gently, with language itself, the way we did once before in an earlier story from this channel, because I think it helps, once more, to notice how our ordinary words strain and stretch when we try to use them to describe something as extreme as a black hole. We've used the word inside quite a lot tonight. What's inside a black hole? What's inside the event horizon? But inside, like so many of our everyday words, was built by human minds navigating an ordinary, human-scale world. A world of rooms and boxes and containers, where inside simply means enclosed within a boundary you could in principle walk back out of if you chose to. Inside a black hole's event horizon, this ordinary meaning of inside begins to strain and shift in genuinely strange ways. As we discussed earlier, once you cross the event horizon, every direction that would ordinarily be called outward instead leads only further inward, the way every direction from the North Pole points south. Some physicists have pointed out that in a strange technical sense, once you're inside a black hole's event horizon, moving toward the singularity isn't simply a choice you could resist by trying hard enough, or by firing powerful enough rocket engines. It becomes, in a certain very real sense, less like a direction in space and more like a direction in time, as inevitable and as impossible to reverse as the forward flow of time itself feels to us in ordinary life. You cannot choose not to move forward into next Tuesday, no matter how hard you try. In a similar way, once inside a black hole's event horizon, you cannot choose not to move toward the singularity. This is a genuinely strange, mind-bending idea, and I don't share it to unsettle you, but rather, again, to offer you permission to hold these ideas loosely, without needing to fully, comfortably grasp them before you're allowed to rest. Our ordinary language, built for an ordinary, human-scale world, were simply never designed to smoothly describe a region of the universe where space and time themselves seem to swap some of their usual familiar roles. Poets and mystics have long understood that language eventually fails, gently, at the very edges of the deepest, strangest experiences. Physicists, working with the very best mathematics human beings have ever developed, are discovering something remarkably similar, arriving at the same soft, humbling edge from an entirely different direction, only to find the same quiet, unanswerable hush waiting there for them too. You get to rest in that hush now, tonight, without needing a single, perfectly precise word to carry you the rest of the way towards sleep. Let's walk gently through a few more of the specific ideas physicists have proposed over the years in their patient attempts to understand what might really be happening inside, or instead of, a classical singularity. Not because any of these ideas are fully settled or proven, but because I think there's something soothing in simply seeing the range and creativity of careful, serious attempts to solve one of physics's hardest remaining puzzles. One such idea, arising from string theory, is sometimes called the fuzzball proposal, developed largely through the work of physicist Samir Mather and his collaborators. In this picture, a black hole isn't truly a region of empty space surrounding a single, infinitely dense point at its center. Instead, according to the fuzzball proposal, what we think of as a black hole's interior is actually filled all the way out nearly to the event horizon, with an extraordinarily complex, tangled configuration of extended, string-like objects, the fundamental building blocks proposed by string theory, replacing the sharp, problematic singularity with something more like a dense, intricately structured, fuzzy ball of stringy material, extending all the way to the horizon itself. If the fuzzball proposal is correct, it would elegantly help resolve the information paradox we discussed earlier, since information wouldn't need to be lost inside a hidden singularity at all. It would simply be encoded in enormously scrambled and complex form within the detailed structure of the fuzzball itself, near the surface, gradually leaking back out as Hawking radiation over time. A different, though related, idea, proposed by physicists Ahmed Alfhiri, Donald Marolf, Joseph Polchinski, and James Sully, suggested something even stranger, sometimes called the firewall hypothesis. This idea proposed that, contrary to our earlier, gentler discussion about falling smoothly and unremarkably across the event horizon, an observer falling into certain black holes might instead encounter an intensely energetic barrier right at the horizon itself, a genuine wall of fire, effectively destroying anything that touched it, rather than allowing a smooth, gentle passage inward. This idea was proposed specifically because certain careful calculations, related once again to the information paradox, seem to suggest that maintaining full consistency with quantum mechanics might actually require such an abrupt, dramatic boundary, rather than the smooth, unremarkable crossing we described earlier tonight. The firewall idea sparked intense, genuinely passionate debate among physicists, precisely because it seemed to directly contradict one of general relativity's most cherished elegant principles, the idea that free-falling observers should notice nothing special or dramatic as they cross an event horizon. This tension between general relativity's smooth predictions and quantum mechanics' more troubling calculations remains, honestly, unresolved, an active area of vigorous, careful research and debate. I share both of these competing ideas with you tonight, gently, side by side. Not because I want you to worry about which one is correct, but because I think it's genuinely soothing to notice how physicists handle deep uncertainty, not with despair, and not by simply making up a comfortable answer and pretending it's settled, but by carefully, patiently proposing multiple possible solutions, testing each one rigorously against the others, remaining humble and honest about which parts are solid, and which parts remain genuinely open. You don't need to decide, tonight, whether fuzzballs or firewalls, or some entirely different idea not yet proposed by anyone, correctly describes what's really happening inside a black hole. You simply get to rest, tonight, in the good company of careful, patient uncertainty, trusting that these questions continue to be worked on, gently and rigorously, by people who have devoted their whole careers to exactly this kind of patient, careful not knowing. Let's take a slower detour now, out across human history and imagination, because black holes, in their own strange way, touch something very old and very human: our long, patient relationship with darkness itself, and with the boundaries between the known and the unknown. Long before modern physics, human beings across many cultures told stories about places from which nothing could return, about boundaries separating the world of the living from realms beyond ordinary experience. In ancient Greek mythology, the underworld was often described as surrounded by rivers that the dead could cross but never recross, most famously the river Styx, its dark waters marking an irreversible boundary, not unlike, in a poetic sense, the one-way nature of a black hole's event horizon. In many indigenous traditions across North America, stories describe places of deep darkness or deep water associated with transformation and passage, thresholds between one state of being and another, echoing, in their own cultural language, that same old human fascination with boundaries that, once crossed, cannot easily be uncrossed. In ancient Mesopotamian mythology, the goddess Inanna's descent into the underworld describes her passing through 7 gates, one by one, gradually stripped of her power and adornments at each threshold, until she reaches the deepest, darkest realm at the center, a slow, patient journey inward that again echoes something of the layered, threshold-crossing structure we've described tonight in a black hole's own architecture, an event horizon, and then, deeper still, a region where our physics itself begins to fail. I don't share these old stories to suggest that ancient storytellers somehow secretly anticipated modern astrophysics. That would be an unfair stretch, flattening the richness of both traditions. Rather, I think there's something worth resting on here gently. That human beings have always been drawn to imagine boundaries between the known and the unknown, thresholds beyond which ordinary rules seem to stop applying, realms of deep darkness holding secrets that can be approached, wondered about, and respected, but never fully, completely mapped. Modern physics, in its own careful mathematical language, continues this very old tradition, describing an event horizon instead of a mythological river, a singularity instead of an underworld's deepest chamber, equations instead of gates and thresholds. But the underlying human impulse, to stand at the edge of the unknown, to wonder gently about what lies beyond, without needing to fully resolve that wondering before finding peace, remains remarkably, comfortingly the same, stretching back across every culture, every century, every quiet night, when someone looked into darkness and felt at once small and curious, and strangely at home. You are part of that very old, very human lineage tonight, resting quietly in the dark, letting old stories and new equations settle gently together, side by side, each one, in its own way, honoring the same deep, patient wonder. Before we move toward tonight's closing passages, I want to share a little, gently, about some of the people behind the ideas we've explored tonight, because I think it helps to remember that every equation, every careful calculation, was worked out slowly, patiently, by real human beings, often uncertain, often doubting themselves, much like anyone might on any ordinary, tiring day. Carl Schwarzschild, a German physicist and astronomer, found the very first exact solution to Einstein's equations describing what we now call a black hole. Remarkably, while serving on the Russian front during the First World War, working out the complex mathematics by hand from within a military camp, sending his careful calculations back to Einstein by letter. He died only a few months later, from a rare illness contracted during his military service, never fully knowing how significant his quiet, careful mathematical work would eventually become. Subramanian Chandrasekhar, an Indian-American astrophysicist, calculated, while still remarkably young, the precise mass limit beyond which a collapsing star's core could no longer support itself against gravity, paving the way for our modern understanding of stellar collapse and black hole formation. His careful, patient calculations were initially met with skepticism and even open hostility from some senior physicists of his time. Yet he continued his careful work regardless, eventually receiving the Nobel Prize in Physics, decades later, for research that had by then become foundational to the entire field. Jocelyn Bell Burnell, while still a graduate student, patiently sifted through enormous amounts of radio telescope data by hand, night after night, and discovered the first pulsar, a rapidly spinning neutron star, a close cosmic cousin to black holes, formed through a similar, though slightly less extreme, stellar collapse. Her careful, patient discovery opened an entirely new window into understanding the dense, extreme objects left behind by dying stars. And the team behind the Event Horizon Telescope, hundreds of scientists and engineers spread across dozens of countries, spent years patiently coordinating an unprecedented global collaboration, working through countless technical challenges before finally producing that historic first image of a black hole's shadow, a quiet, patient testament to what careful, coordinated human effort can accomplish, even when studying something as extreme and remote as a supermassive black hole 55 million light-years away. I share these glimpses with you tonight, not as a history lesson, but as a gentle reminder that the strange extreme physics we've explored tonight was uncovered patiently, carefully, often under difficult circumstances, by real people who also grew tired, who also doubted themselves, who also, presumably, had quiet nights much like this one, their minds still turning over unfinished calculations, before finally, eventually, allowing themselves to rest. Let their patience become your patience now, tonight. Let their careful, quiet persistence remind you that you too are allowed to set down your own thoughts now, gently, and rest. Let's rest a while longer on the physics itself, because there's a detail we've gently glossed over so far tonight, one worth slowing down for. Almost every black hole in the real universe is spinning. When a massive star collapses, it doesn't simply fall straight inward from perfect stillness. Stars, like almost everything else in the universe, rotate, slowly, patiently, throughout their long lives, the way Earth rotates once a day, or the way a figure skater turns slowly at the center of an ice rink. When such a star's core collapses down into a black hole, that rotation doesn't simply vanish. Instead, exactly the way a figure skater spins faster and faster as she pulls her arms in close to her body, a collapsing stellar core spins faster and faster as it shrinks, conserving what physicists call angular momentum. By the time a black hole has fully formed, it may be spinning extraordinarily quickly, in some cases close to the maximum rate that physics itself allows. A spinning black hole is described by a different mathematical solution to Einstein's equations than the simpler, non-spinning kind we've mostly discussed tonight, called a Kerr black hole, after the mathematician Roy Kerr, who worked out this solution in 1963. Kerr black holes behave, in several fascinating ways, differently from their simpler, stationary cousins. For one, a spinning black hole doesn't just curve the space around it inward, toward its center. It also gently drags the surrounding space around with it, in the direction of its spin, a phenomenon called frame dragging. Picture, if it helps, a black hole resting in the middle of a vast pool of thick honey, slowly spinning in place. As it spins, it doesn't just sit passively in the honey. It drags the honey immediately around it into a slow swirling motion too, the effect growing weaker the farther away you look, but never quite vanishing entirely. This frame dragging effect creates a region just outside a spinning black hole's event horizon, called the ergosphere, a strange flattened zone where space itself is being dragged around so forcefully that nothing, not even light, can remain stationary within it, relative to the distant stars, even though, remarkably, it's still technically possible, within the ergosphere, to escape back outward, unlike within the event horizon itself. This peculiar region opens the door to a genuinely fascinating theoretical possibility called the Penrose process, proposed by the physicist Roger Penrose. In principle, an object entering the ergosphere could split into two pieces, with one piece falling into the black hole, while the other piece escapes back outward, carrying away more energy than the original object possessed, effectively extracting a small amount of rotational energy from the spinning black hole itself, very gradually slowing its spin over time. No one has ever observed this process directly, but it remains a mathematically sound, genuinely intriguing possibility, a reminder that even a black hole's rotational energy might in principle someday be gently, carefully tapped. There's also something called the no-hair theorem, a wonderfully evocative name for a genuinely important idea in black hole physics. It states that, no matter how complex or varied the star or matter that originally collapsed to form a black hole, the resulting black hole itself can be entirely described using just three simple numbers: its total mass, its rate of spin, and its electric charge, if any. Every other detail about whatever fell in, its shape, its composition, its history, is, in a sense, forgotten, smoothed away entirely, leaving behind only these three simple properties. Physicists sometimes say a black hole has no hair, meaning no other distinguishing features or textures remain visible from the outside, no matter how intricate or interesting the object that originally created it. I find something quietly poetic in this idea tonight, as your own mind begins to smooth and settle towards sleep. A black hole, however complex its origins, however varied the star or the swirling cloud of gas and dust that gave rise to it, settles eventually into a state of remarkable, almost meditative simplicity. Just three numbers, calm and complete, describing the whole of what remains. There's something in that image worth resting on gently tonight, that even the most complicated beginnings can eventually settle into something simple, quiet, and whole. Let's walk through one more careful, technical idea tonight, gently, because I think it reveals something rather charming about how physicists think about the universe's own hidden rules. We've spent much of tonight discussing the singularity at a black hole's center as something safely hidden, tucked away behind the event horizon, inaccessible to any outside observer. This hiddenness turns out to matter quite a lot to physicists, for a very particular reason. If a singularity, a point of theoretically infinite density and infinite curvature, were ever exposed directly to the outside universe, without an event horizon concealing it, it could, in principle, cause genuinely severe problems for our ability to predict anything at all about the future evolution of the universe nearby, since the ordinary rules of physics simply don't function reliably at a true singularity. To address this concern, the physicist Roger Penrose proposed something called the cosmic censorship hypothesis, an idea that states, roughly, that singularities formed through the realistic collapse of ordinary matter should always be hidden safely behind an event horizon, never exposed directly to the outside universe as what physicists call a naked singularity. In other words, nature itself, according to this hypothesis, maintains a kind of built-in modesty, always keeping its most extreme, most troublesome mathematical features politely concealed from view. It's worth pausing gently here to notice how genuinely strange and genuinely charming this hypothesis is. As a piece of scientific reasoning, it isn't simply a mathematical theorem, proven directly and completely from Einstein's equations. Despite decades of effort, a fully general, rigorous proof of cosmic censorship remains elusive, one of the significant open problems in mathematical physics today. Instead, it functions more like a deeply held, carefully reasoned expectation, strongly supported by everything we currently understand about realistic gravitational collapse, yet still awaiting a truly complete, comprehensive proof. Physicists have explored various theoretical scenarios under highly idealized and unusual conditions, where naked singularities might in principle form. For instance, in certain carefully constructed mathematical models involving very particular, symmetric collapses of matter. But it remains genuinely uncertain whether any of these idealized scenarios could actually occur under the messy, realistic conditions of our actual universe, where perfect symmetry essentially never truly exists. I share this rather technical corner of black hole physics with you tonight, because I think it captures something quietly beautiful about how careful science proceeds. Even a hypothesis with a playful, almost old-fashioned name, like cosmic censorship, reflects a genuinely serious, patient, ongoing effort to understand the deep, hidden rules governing our universe's most extreme structures. An effort that, like so much of tonight's story, remains carefully, honestly unfinished, a puzzle still being worked on, gently and rigorously, by people devoted to exactly this kind of patient uncertainty. Rest with this idea for a while now, gently. Even at its most extreme, the universe seems to prefer a certain quiet modesty, keeping its sharpest, most troublesome edges politely hidden away, tucked behind soft, protective boundaries, much the way your own mind right now is gently tucking away the sharper edges of today's worries, hidden softly behind the approaching protective boundary of sleep. Let's spend a little more time now with one of the most remarkable events the universe can produce: the slow, patient, and ultimately dramatic meeting of two black holes, spiraling gradually together across unimaginable spans of time, until, in one final, brief instant, they merge into one. Picture two black holes, each many times the mass of our Sun, born from separate, massive stars that lived and died long ago within the same general region of a distant galaxy. Perhaps they formed as a binary pair from the very beginning, two massive stars orbiting each other closely throughout their lives, each eventually collapsing into its own black hole while remaining gravitationally bound to its companion. For a very long time afterward, these two black holes might simply continue orbiting one another, slowly, patiently, at a comfortable distance, much the way two dancers might slowly circle each other across a vast, quiet ballroom floor. But their orbit isn't perfectly stable, not over sufficiently long timescales. As the two black holes orbit each other, they continuously radiate faint gravitational waves outward into space, ripples in space-time itself, carrying away a tiny, tiny amount of orbital energy with each pass. This loss of energy is so gentle, so gradual, that for most of their long orbital dance, it makes essentially no noticeable difference at all. But slowly, patiently, across millions or even billions of years, this gentle radiation causes the two black holes to spiral very gradually closer together, their orbit tightening, almost imperceptibly, year after year, century after century. As the two black holes finally draw close, in the last moments before their eventual merger, everything begins to happen much more quickly. Their orbital dance speeds up dramatically, faster and faster. The two black holes whipping around each other at speeds approaching a significant fraction of the speed of light, radiating gravitational waves far more intensely than before, until, finally, in a final, brief, dramatic instant, their event horizons touch and merge and become one single, larger black hole, releasing an almost unimaginable burst of energy outward in the form of gravitational waves in just a fraction of a second. An amount of energy that can briefly exceed the combined light output of every star in the observable universe, though released, remarkably, not as light at all, but purely as ripples in the fabric of space-time itself. This is precisely the kind of event that instruments like LIGO were built to detect, listening patiently for years, for the extraordinarily faint final chirp of two black holes merging somewhere out in the depths of the universe, a signal that rises rapidly in both pitch and intensity in its last fraction of a second, the unmistakable signature of two massive objects spiraling together, and finally, dramatically, becoming one. Since that first historic detection in 2015, LIGO and its partner observatories around the world have detected dozens upon dozens of these black hole mergers, each one a distant, patient love story of sorts. Two massive objects drawn gradually together across unimaginable spans of cosmic time, before finally, briefly, dramatically, becoming one, their gentle, final ripple traveling outward for millions or even billions of years afterward, before finally, quietly, reaching our small, patient instruments here on Earth. There's something I find quietly moving in this image tonight, something worth resting on gently as you drift toward your own kind of quiet rest. Even the darkest, most extreme objects in the universe are drawn slowly and patiently toward union, toward joining, toward becoming something new and whole. Their long, gradual dance ending, not in destruction exactly, but in a kind of profound, final merging, releasing one last, brilliant burst of energy outward into the waiting universe, before settling finally into a new, quiet, singular existence. Let that image rock you now, gently, the way two distant dancers might slowly draw closer together across a vast, quiet floor, their movements gradually softening, gradually merging into one single, final, peaceful stillness. Before we return, finally, to rest, let's pause for a while with a close cosmic relative of the black hole, an object that helps, gently, to illustrate just how extreme a black hole truly is. By comparison, the neutron star. Remember our story from earlier tonight about a massive star's core collapsing inward once its nuclear fuel runs out? We described how, if that collapsing core is massive enough, nothing can stop its collapse, and it forms a black hole. But there's an important, gentler middle step in this story, worth resting on for a while. For cores that are massive, but not quite massive enough to become a black hole, the collapse can instead be halted by an extraordinary, almost unbelievable form of resistance, forming an object called a neutron star instead. Here's how this gentler halt happens. As a stellar core collapses, its atoms are crushed together with such overwhelming force that electrons are pushed directly into protons, combining to form neutrons and releasing tiny, nearly massless particles called neutrinos in the process. The core, in this way, transforms into an object made almost entirely of tightly packed neutrons. And it's here that a strange and wonderful quantum mechanical principle finally steps in to halt the collapse. A rule called the Pauli exclusion principle, which states roughly that no two identical particles, like neutrons, can occupy the exact same quantum state in the same place at the same time. This creates an immense, almost unimaginable outward pressure, called neutron degeneracy pressure, powerful enough for cores below a certain mass to finally halt the relentless inward pull of gravity, holding the collapsing star up, at last, against its own immense weight. The result is genuinely one of the strangest objects in the observable universe. A neutron star typically has a mass somewhere between 1 and 2 times the mass of our Sun, and yet it's compressed into a sphere only about 20 kilometers across, roughly the size of a modest city. A single teaspoon of neutron star material, if you could somehow bring it back to Earth, would weigh, astonishingly, about as much as a mountain, its matter compressed to a density comparable to that of an atomic nucleus itself, spread out across an entire star. Neutron stars often spin extraordinarily quickly, sometimes hundreds of times per second, a natural consequence, once again, of that same conservation of angular momentum we discussed earlier with spinning black holes. Some neutron stars, called pulsars, emit narrow, powerful beams of radiation from their magnetic poles, sweeping around like a cosmic lighthouse as the star spins, briefly flashing toward Earth once with every rotation, allowing astronomers to detect them as remarkably precise, rhythmic pulses of radio waves, some of the most accurate natural clocks known anywhere in the universe. If you were to gently increase a neutron star's mass, adding matter to it bit by careful bit, you would eventually reach a point, somewhere around 2 to 3 times the mass of our Sun, beyond which even that extraordinary neutron degeneracy pressure can no longer hold back gravity's relentless pull. Past this point, the collapse resumes, and there is nothing else left in the arsenal of known physics to stop it. This final, complete collapse is what produces a black hole. I find something quietly instructive in resting on this comparison tonight. A neutron star represents, in a sense, matter pushed right up to the very edge of what our universe's ordinary physics can support. An object so dense, so extreme, that it would have seemed like pure fantasy to physicists only a century ago, and yet it still, remarkably, remains just this side of the final, complete collapse into a black hole. A black hole, then, isn't simply more extreme in a vague general sense. It represents a genuinely qualitative leap beyond even the most extreme configuration of ordinary matter that physics allows. A point where every known form of resistance has been fully, completely exhausted, and gravity, at last, wins entirely and finally. Picture, if it helps you settle further into sleep, this gentle, patient hierarchy. An ordinary star, held up by the outward push of fusion. A white dwarf, the quiet remnant of a smaller star, held up by the resistance of tightly packed electrons. A neutron star, held up by the even more extraordinary resistance of tightly packed neutrons. And finally, a black hole, where every form of resistance has been overcome, and only gravity itself remains, complete and total, curving space into that deep, patient well we've spent so much of tonight exploring. Each step in this hierarchy represents a slightly different, slightly more extreme way that matter can respond to the relentless pull of its own gravity. And there's something soothing, I think, in seeing black holes, not as some isolated alien anomaly, but as simply the final, most complete step along a long, gradual, and genuinely well-understood continuum. One careful stage building patiently upon the last. Let's pause, gently, for one more quiet, reflective moment before we turn, finally, towards sleep. A chance to simply sit with the strange, patient presence of a black hole itself. The way you might sit quietly beside an old, wise, silent figure, not expecting conversation, but comforted simply by their steady, patient presence nearby. If you could somehow ask a black hole a question and somehow expect a reply, what might you ask? Perhaps you'd ask what it remembers of the star it once was, back when it still shone brightly, warming worlds that may have orbited it before its long collapse began. Perhaps you'd ask what it has witnessed, drifting silently through its galaxy for millions or billions of years, gently gathering in gas and dust, occasionally merging with a companion, watching, in its own strange way, the slow unfolding of cosmic history all around it. Of course, a black hole cannot answer. Not in any way we could understand. It has no mind, no memory in any sense we would recognize, no voice with which to reply. And yet, in another sense, in the strange, careful language of physics, a black hole does hold a kind of memory, doesn't it? We talked about this earlier tonight, how information, according to our best current understanding, is never truly lost, only scrambled and eventually, slowly, returned to the universe through Hawking radiation, across achingly long spans of time. In this sense, a black hole is less like a silent, forgetful void, and more like an extraordinarily patient, extraordinarily careful archive, holding everything that has ever fallen into it, however scrambled, however slowly it might eventually give that information back. There's a quiet comfort, I think, in imagining a black hole this way tonight, not as an object of destruction or loss, but as a kind of patient keeper, holding vast stretches of cosmic history within itself, gently, carefully, for however many trillions of years it takes, before finally, eventually, returning what it holds back to the wider universe, in some deeply transformed, deeply scrambled, but ultimately still preserved form. Perhaps, if you could ask a black hole anything at all, the most honest answer it could offer wouldn't be in words, but simply in its own patient, continued existence. Here I am, it might say, without speaking, holding what has been given to me, changing it slowly, carefully, according to rules deeper than anyone yet fully understands, asking nothing in return, offering nothing back, except, eventually, in the fullness of unimaginable time, a slow, gentle release. There's something in that quiet, patient image worth carrying with you now, into your own rest tonight. You too are holding things today, thoughts, worries, small unfinished tasks, fragments of conversations, moments from your day that haven't quite settled yet. You don't need to sort through any of them right now. You can simply hold them gently, the way a black hole gently, patiently holds everything that has ever fallen into it, trusting that, in their own time, in their own way, they will settle and transform, and eventually, quietly, release themselves from your attention, long after you've drifted off to sleep. Let yourself be for a little while tonight, as patient and as quiet as one of these strange, ancient, silent objects, holding everything gently, asking nothing urgent of yourself, simply resting, simply being, simply here. Let's slow all the way down now, together, and rest for a while in your own body, letting the physics settle quietly into the background, like a soft, distant hum, while we attend instead to something closer, something warmer, the simple, quiet fact of you, breathing, right here, right now. Feel the weight of your body resting gently against your mattress, held in place by Earth's own soft, familiar curve in space-time. Nothing at all like the steep, extreme well surrounding a black hole, just a gentle, comfortable dip, holding you kindly in place. The same fundamental gravity that shapes galaxies and black holes, also gently, patiently, keeping you exactly where you are right now. Notice your breath, moving in and out, slow and steady. Notice how, unlike an object trapped forever behind an event horizon, your breath moves freely, in both directions, out into the world and back into your body again, over and over. A small, private, endlessly reversible rhythm. Nothing at all like the one-way boundary we've spent so much of tonight discussing. Feel your heartbeat, if you can sense it at all, keeping its own small, steady time, entirely independent of the strange, stretched, dilated time near a black hole's horizon. Simply your own gentle, ordinary rhythm, carrying you softly, minute by minute, towards sleep. Let your shoulders soften now, a little more. Let your hands go loose and heavy, resting easily, holding nothing, needing to grip nothing. Let your legs feel heavy too, sinking gently into your mattress, the way matter, long ago gently settled into the shallow gravitational wells that eventually became stars and planets. Though your own settling tonight need be nowhere near so dramatic, just a soft, comfortable sinking into rest. Let all of tonight's strange, wonderful ideas sink gently away now too, one at a time. The way you might release smooth stones back into still, quiet water, watching each one sink slowly out of sight, leaving behind only a few soft ripples, spreading outward, and then, eventually, smoothing back into stillness. Let the collapsing star sink away now. Let the event horizon and its strange, one-way boundary sink away. Let the stretching and the bending and the singularity, still quietly unmapped, sink away. Let the information paradox and the fuzzballs and the firewalls sink away. Let the ancient stories of rivers and gates and thresholds sink away. Let all of it go, gently, ripple by soft ripple, until only stillness remains. Only your breath, only your heartbeat, only the quiet dark around you, patient and unhurried, asking nothing of you now except rest. Let's rest for a while longer on something real and observed, one more concrete, gentle story from the universe itself, before we turn fully towards sleep. The slow, strange farewell of a star that wanders too close to a supermassive black hole. Every so often, in some distant galaxy, a star's long, ordinary orbit carries it a little too close to the supermassive black hole resting quietly at its galaxy's center. As the star drifts nearer, the black hole's tidal forces, the same gentle stretching we discussed earlier tonight, begin to grow stronger and stronger, pulling more forcefully on the near side of the star than on its far side. If the star passes close enough, these tidal forces can eventually overwhelm the star's own gravity, the very gravity that has held it together, quietly and patiently, for its entire life, and the star begins, slowly, gently, to come apart. Astronomers call this a tidal disruption event, and remarkably, we've actually observed several of these rare dramatic farewells directly, using telescopes here on Earth. As the star is gradually torn apart, roughly half of its stretched, disrupted material is flung outward, escaping the black hole's pull entirely, drifting off into the surrounding galaxy. But the other half spirals inward, gradually forming a bright, glowing disk of superheated gas around the black hole, radiating an enormous, sudden flash of light and radiation, sometimes bright enough to briefly outshine the entire rest of the star's home galaxy. A final, brilliant flare marking what was once an ordinary, steadily shining star. Astronomers watching through their telescopes see this event unfold gradually, over weeks or months, the flare slowly rising to its peak brightness, and then, just as slowly, fading away again, as the disrupted star's remaining material either falls fully into the black hole or gradually settles into a colder, quieter orbit around it. It's a genuinely strange thing to consider. Astronomers, sitting quietly at their instruments, patiently watching the light from a star's final, slow gravitational farewell, arriving after having traveled across millions or even billions of years of empty space to finally reach us. I find something quietly moving in resting on this image tonight. One more concrete, observed reminder that everything we've discussed tonight, however strange, however extreme, is woven into the real, ongoing life of our universe. Stars are born and live, and eventually, in one way or another, come to their own particular ending. Some fading gently, some exploding brilliantly, and some, on rare occasions, drawn slowly, gently apart by the patient, overwhelming pull of a supermassive black hole they wandered too close to. their final light still reaching us, patiently, gently, long after the event itself has already finished unfolding, somewhere impossibly far away. There's a kind of grace, even in this, I think, worth resting on gently tonight. Nothing in the universe simply vanishes without a trace. Even a star's final dramatic unraveling becomes eventually part of the quiet architecture surrounding a black hole. Its material either scattered gently back out into its home galaxy, or settling slowly into a new glowing disk, contributing in its own small way to the black hole's continued, patient existence. Let this image settle over you now, gently. One more soft reminder that the universe's most extreme events are not chaotic or without pattern, but are instead governed by careful, knowable, deeply beautiful physics, unfolding slowly, patiently, exactly as the equations predict, watched over quietly by careful telescopes and even more careful, patient scientists. Let's spend a little more time, gently, with something wonderfully close to home before we turn, finally, towards sleep. The supermassive black hole resting quietly at the very center of our own galaxy, the Milky Way, the same galaxy that holds our Sun, our Earth, and you, resting right now, safely, tens of thousands of light years away from its dark, quiet heart. Astronomers first became confident that something extraordinarily massive, yet completely invisible, lay at the center of our galaxy by patiently watching a small cluster of stars near the galactic core, tracking their motion year after year, decade after decade, with extraordinary care and precision. These stars, orbiting an apparently empty point in space, moved in ways that could only be explained by the gravitational influence of an object roughly 4 million times the mass of our Sun, compressed into a region smaller than our own solar system. This patient work, carried out over more than 2 decades by 2 independent teams of astronomers, led by Reinhard Genzel and Andrea Ghez, eventually earned both scientists a share of the Nobel Prize in Physics, awarded for their careful, painstaking confirmation that our galaxy's center truly does harbor a supermassive black hole, now known as Sagittarius A. One particular star in this region, nicknamed S2, completes an entire orbit around this invisible giant in just over 16 years, swinging, at its closest approach, to within a distance smaller than the size of our own solar system, moving at that point at several percent of the speed of light. An extraordinary, real, directly observed confirmation of gravity's extreme behavior near a genuinely massive black hole. As we mentioned earlier tonight, in 2022, astronomers finally captured a direct image of Sagittarius A star itself using the Event Horizon Telescope, revealing the same faint, glowing ring surrounding a dark central shadow that had earlier been captured around the black hole in the distant galaxy Messier 87. Seeing this familiar shape, this same gentle silhouette, at the heart of our own galaxy, rather than in some far more distant one, offers a particular kind of quiet, grounding wonder, I think. A reminder that we too live in a galaxy with its own dark, mysterious, deeply patient heart, resting quietly at the center of everything, tens of thousands of light years away, entirely undisturbed by the small, ordinary lives unfolding gently across its outer spiral arms, where our own solar system quietly resides. There's no need for any concern here tonight. I want to gently reassure you. Sagittarius A Stief poses no danger whatsoever to Earth or to our Sun. It's far too distant, and our own solar system's orbit around the galaxy's center is far too stable, gentle, and well established for any dramatic encounter to ever occur. It simply rests there, quietly, at the center of our galactic home, a silent, patient anchor point, around which our entire galaxy slowly, gracefully turns, once every couple 100 million years. An enormous, majestic, unhurried rotation that has been continuing steadily since long before Earth itself even formed. I find something quietly beautiful in resting on this thought tonight, that our own galaxy, home to hundreds of billions of stars, including our own quiet Sun, gently orbits, generation after generation, around a supermassive black hole at its center. The very same kind of object we've spent this entire story exploring. You are right now, tonight, slowly, gracefully orbiting a black hole yourself, along with everything else in our galaxy, at a perfectly safe, perfectly gentle distance, carried along by the same patient physics that governs stars and planets and the graceful, curved architecture of space-time itself. Let that thought settle over you now, like a final, quiet reassurance. You are held, right now, not only by Earth's own gentle gravity, tucking you softly into your bed, but by the vast, slow, graceful turning of an entire galaxy, curving gently around its own quiet, patient heart, carrying you and everyone you have ever known softly through the cosmos, in an orbit so vast, so slow, so patient that it will not complete even a single full turn within your entire lifetime. As we near the end of tonight's story, I want to gather together, gently, one more time, everything we still don't fully know about black holes, not as a list of failures or frustrations, but as an honest, quiet inventory of the genuine mystery still remaining, out there, patient and unsolved, in the dark. We don't know, with full confidence, what truly exists at a black hole's very center, whether a true singularity or some far stranger structure, a fuzzball, a bounce into a new region of space-time, or something not yet imagined by anyone. We don't have a complete, tested theory of quantum gravity capable of fully describing physics at such extreme densities. We don't know, with total certainty, exactly how information is preserved as a black hole slowly evaporates, though we have good theoretical reasons to believe it must be. We don't know whether the firewall hypothesis or the fuzzball proposal, or some entirely different idea, correctly describes the true nature of the event horizon at the deepest quantum level. We don't know whether traversable wormholes could ever truly exist, connecting distant points in space. We don't fully understand how supermassive black holes managed to grow so large, so quickly in the early universe. This is a genuinely long list of open questions, and I offer it to you tonight, not to overwhelm you, but because I think there's something quietly wonderful in an honest, complete accounting of uncertainty, rather than a tidied up, falsely confident story. Real science at its very best looks exactly like this: a patient, careful, ever-growing list of open questions, worked on steadily, generation after generation. Each answer typically revealing 2 or 3 new questions in its place. The frontier of knowledge continually pushing outward, the way ripples continue spreading outward across a pond, long after the original stone has settled quietly to the bottom. You get to rest tonight inside this honest uncertainty, trusting that it represents not a failure of human understanding, but rather its ongoing, healthy, patient growth. The mystery of what's truly inside a black hole will still be there tomorrow, and the year after that, and quite possibly for many years or even decades beyond that, patiently waiting for careful scientists to continue their slow, steady work. You don't have to hold any of it yourself tonight. You only have to rest, trusting, gently, that the mystery is being tended to, carefully and patiently, by people whose whole careers are devoted to exactly this kind of quiet, unfinished wandering. We're nearing the end of our quiet museum now, so let's walk, one final time, softly, back through the rooms we've visited together tonight, not to study them again, but simply to say a gentle goodbye to each one, the way you might walk once more through a house before turning off all its lights. In the first room, we watched a massive star's core collapse quietly inward, past every point where any known force could stop it, forming, at last, an invisible boundary in space, an event horizon. In another room, we stood at that very boundary, learning that it isn't a wall at all, but a point past which every direction leads only inward, the way a whirlpool's current eventually overwhelms even the strongest swimmer. We fell gently, in our imaginations, toward a black hole, discovering the strange mismatch between what a falling observer experiences and what a distant, watching friend would see, time stretching and slowing in ways that ordinary intuition never quite prepared us for. We visited a room explaining spaghettification gently and carefully, learning that not every black hole treats a falling object the same way, that scale and size matter, even at the very extremes of physics. We stood once more at the edge of a map, marked "Here be dragons," honoring the honest limits of our current equations at a black hole's singular, still unmapped center. We wandered through a careful catalogue of black hole types, stellar and supermassive and primordial, sorted gently, like smooth stones on a quiet shelf. We sat with the information paradox and the slow, patient fading of Hawking radiation, and the strange, beautiful holographic idea that our whole three-dimensional world might be a kind of projection from a simpler, flatter surface. We considered wormholes gently, as elegant but likely unrealized shortcuts through the fabric of space. And we admired real telescopes and real instruments that have actually seen a black hole shadow, actually felt the ripple of two black holes colliding long ago and far away. We visited fuzzballs and firewalls, careful, competing guesses at the true nature of a black hole's interior. And we wandered through old human stories of rivers and gates and thresholds, echoing, across centuries, the very same wonder we carry with us tonight. We spent time, too, with spinning black holes, dragging space itself around them, like honey swirling around a slow, turning spoon, and with the quiet, modest hypothesis that nature prefers to keep its sharpest mathematical edges politely hidden away, tucked behind protective horizons. We watched, gently, as two distant black holes spiraled slowly together, across unimaginable spans of time, before finally merging into one, releasing a brief, brilliant ripple across the fabric of the universe itself. We visited neutron stars too, a near miss, matter pushed right to the very edge of what ordinary physics can support. And we sat quietly for a while, imagining what a black hole might say, if it could ever answer, holding everything gently, offering nothing back, except, eventually, in the fullness of time, a slow, patient release. We watched too, a distant star's slow, gentle farewell, gradually torn apart by tidal forces, its final light still arriving patiently across millions of years to reach our own quiet telescopes. And we rested finally, with the quiet giant at the very center of our own galaxy, Sagittarius, a star patiently anchoring the slow, graceful turn of hundreds of billions of stars, our own sun and Earth included, carrying you gently through the cosmos even now, in an orbit far too vast and far too slow to ever complete within a single lifetime. Every room in this quiet museum stays exactly where it is, waiting patiently for you, whenever you'd like to visit again, tomorrow night or any night after that. Nothing you've heard tonight needs to be carried forward into tomorrow. You can leave all of it here gently in these quiet rooms and simply walk out now, into the dark hallway, and from there, into sleep. All of these ideas we've explored tonight, collapsing stars and event horizons, stretched and dilated time, singularities marked unknown on the very edge of our maps, information quietly preserved in slow, fading radiation, holograms and wormholes, fuzzballs and firewalls, ancient rivers and gates. All of these ideas, as vast and strange as they are, live inside something small and warm and entirely human, the quiet, patient curiosity of people who simply wanted to understand. Physicists studying black holes are not so different in a way from a child lying in the grass on a summer evening, looking up at the first stars appearing in a darkening sky, and asking quietly, "What's out there, in the dark, that I can't quite see?" The mathematics has grown enormously sophisticated, the instruments enormously precise, but underneath all of it is the very same simple wonder, the very same soft, patient curiosity you might have felt yourself as a child, or might be feeling right now, tonight, as you drift towards sleep. You don't need a degree in physics to feel connected to this story. You don't need to fully understand the mathematics behind Hawking radiation, or the holographic principle, or the firewall hypothesis, to feel the same quiet awe that drove the physicists who developed them. The wonder comes first. The mathematics comes later, built carefully on top of that first simple feeling of looking into darkness and gently asking what might be there. So tonight, let yourself feel that wonder, gently, without needing to chase it any further than feels comfortable. You have traveled, in your mind, across some of the strangest, most extreme corners of the known universe, places where time bends, where light itself can become trapped forever, where our very best equations quietly admit their own limits. And that's all right. The traveling itself, the wondering itself, is enough. Somewhere out there right now, scattered across our galaxy and countless others, Black holes drift silently through the dark, ancient, patient, unhurried, holding their deepest secrets quietly, waiting, perhaps, for physics itself to grow patient and careful enough, someday, to finally understand them fully. You get to rest inside all of that tonight. Small, warm, safe, held gently within a universe so vast and strange that even its darkest objects remain, after a century of careful study, genuinely, wonderfully mysterious. Let your body grow heavier now. Let your thoughts grow softer, slower, quieter. If you like, picture yourself once more as that child lying in the summer grass, looking up at a darkening sky, unafraid of its shadows, simply curious about them. Feel the cool ground beneath you, the last warmth of the day still rising gently from the earth. Notice how the darkness doesn't ask you to understand it completely in order to feel safe within it. It simply spreads out above you, wide and deep, and gently mysterious, patient, and unhurried. Exactly as it has for longer than anyone can easily imagine, and exactly as it will continue to be long after tonight, long after you wake tomorrow. You don't need the answer to rest peacefully beneath that sky, or above that hidden, unmapped darkness. You never did. The wondering itself, held loosely, held gently, without urgency, without struggle, is enough. It always has been. We're nearing the very end of tonight's journey now, so let's slow all the way down, together, the way a long, winding river finally widens and slows as it nears the quiet sea. We began by wondering what's truly inside a black hole. We walked gently through the slow, patient collapse of a dying star and the strange, invisible boundary that collapse creates. We considered what it might be like to fall toward one, and how time itself stretches and bends near its edge. We learned that not every fall feels the same, that scale and size shape the experience gently, carefully. We stood once more at the honest edge of our current equations, admitting plainly that the deepest center of a black hole remains genuinely unknown. We wandered through the different families of black holes and sat with the strange, hopeful puzzle of the information paradox and the slow, patient fading of Hawking radiation across trillions of years. We considered holograms and wormholes and real telescopes that have truly seen a black hole's shadow. We weighed fuzzballs against firewalls and let old human stories of rivers and thresholds settle gently alongside new, careful equations. None of these ideas on their own are certainly completely proven, especially not at the deepest, most extreme heart of a black hole. And that's all right. That's simply where the edge of human knowledge currently stands. And it's a beautiful, humbling place to rest together tonight. You don't need to remember any of the details now. Let them all blur softly together, the way a painting blurs when you take off your glasses, colors bleeding gently into one another, shapes softening, edges dissolving, collapsing stars and slow glowing rings of gas, stretched and dilated time, a quiet, patient not knowing, resting easily in your chest instead of pressing anxiously against it. Feel your body now, heavy and warm against the mattress beneath you. Feel your breathing, slow and even, rising and falling like some small, quiet universe of its own, expanding gently with each inhale and softly contracting with each exhale. In and out, in and out. There is nothing you need to do right now except rest. Nothing you need to figure out, nothing you need to solve. Black holes have kept their deepest secrets for billions of years. They can certainly keep them a little longer while you drift off to sleep. Let your eyelids grow heavier. Let your thoughts grow softer, farther apart, the way stars grow farther apart as the universe expands, the space between each thought stretching gently, slowly, comfortably, until the thoughts themselves grow quiet and distant, and eventually fade. Before we count down together, let's take one more slow, unhurried breath, and let one final image settle over you gently. Imagine you are floating, weightless and entirely safe, not falling toward anything at all, simply drifting in the calm, dark quiet of open space, far from any event horizon, far from any tidal pull, with nothing around you but soft, scattered starlight and an enormous, patient silence. There is no urgency in this darkness, No pull demanding your attention, just quiet and stillness, and the gentle, distant twinkle of stars so far away that their light has been traveling toward you for longer than you can easily imagine, arriving now, softly, patiently, asking nothing of you except that you notice it, just for a moment, before letting your eyes close completely. Let's count that quiet down together now, slowly, the way you might count slow, easy breaths, with nowhere else to be. 1. A quiet room, dim and warm, holding you exactly as you are. 2. A slow breath in, filling your chest gently, without effort. 3. A slower breath out, releasing anything you've been holding onto today. 4. Your eyelids, heavier now, resting fully closed. 5. Your shoulders, sinking a little further into the mattress beneath you. 6. Your hands, open and still, asking nothing of the world right now. 7. Your whole body, settling, the way dust settles slowly through still water, drifting down, down, gently down, into quiet. 8. And just breathing now. Nothing to solve, nothing to hold, nothing to figure out before you're allowed to sleep. You don't have to know what's inside a black hole tonight. You only have to rest. Somewhere out there, in the quiet dark between the stars, those strange patient objects continue holding their secrets, unhurried, exactly as they have for longer than anyone can easily imagine. Somewhere, tens of thousands of light years from where you're resting right now, the quiet giant at our own galaxy's heart continues its slow, silent watch, asking nothing of you, offering nothing but its patient, distant gravity, gently guiding our whole galaxy through its long, unhurried turn. Let yourself be just as patient, just as unhurried. Slowly, gently, safely. Drifting now, softly, into sleep, the way light itself, at the very edge of a black hole, drifts slowly, gently, toward a horizon it will never quite need to cross tonight. Good night.